Hello everyone, and thanks for joining. My name is Balint. I work at ARM in the Trusted Services team, and in these last few months, one of my tasks was to implement a firmware TPM in the Trusted Services project. To be more specific, it is a TPM service running in a secure EL0 FFA secure partition that implements the standard TPM CRB over FFA communication interface. And I know that's a lot of three-letter acronyms, so in the first half of the presentation I would like to take a step back and give an overview of the various building blocks that enable this use case. And then we will move on to the actual implementation and end-to-end testing, like what other components you need in your system to do that. Then I will briefly talk about an ongoing investigation related to replacing the crypto library in MSTPM with PSA Crypto API calls and the challenges with this. And finally, I want to mention how this work relates to the OPTI fTPM TA. Let's start with FFA. It's the firmware framework for ARM A profile. It's a specification by ARM, and it standardizes the software architecture of the firmware components. So it mostly concerns everything outside of the normal world OS and its user space. The two components that are interesting for us today are the Secure Partition Manager and the Secure Partitions. So the Secure Partition Manager, the SPM, it's split into two parts. One is the SPMD, which is part of the EL3 runtime firmware, and it's responsible for switching between secure and non-secure words and also forwarding messages between these. The SPMC, the Secure Partition Manager core, that's kind of like a secure hypervisor that can manage secure partitions, or SPs. The SPs are a isolated execution environment that can run a secure service, and it can either run in secure EL1 when it can host a full trusted OS like OPTI or Trusty, which in turn can run its own applications in EL0. Or you can have a secure EL0 SP, in which case it only contains an application and it's directly managed by the SPMC. So FFA provides a standardized way for these components to communicate with each other by providing a register API for the messages, some primitives for doing memory sharing, discovery mechanism, and so on. The Trusted Services project, it's a collection of secure EL0 SPs. And first it was started as the reference implementation for PSA services on A profile. But during the years, it has been extended with various other services. And one of those now is the fTPM. So what is a TPM? It stands for Trusted Platform Module. And first of all, it's a standard by the TCG, which is the Trusted Computing Group, and it defines a hardware root of trust. So it describes what operations it should provide, how you can access it, what functions and algorithms it should implement. And there are various ways to implement this specification. The most well-known is a discrete TPM, when the TPM is a standalone chip that you can buy, solder on your board. And usually this also provides some mitigation against physical attacks. The integrated TPM, when the TPM is integrated into a larger chip like a desktop CPU. The firmware TPM, when the TPM software is running in a trusted execution environment like ARM Trust Zone. And the virtual TPM when it's provided by the hypervisor. So I've listed some features and use cases of a TPM. This is not an exhaustive list. And first of all, I want to highlight that TPM is not a generic crypto accelerator. It provides some crypto operations, but those are for specific purposes. So you can use a TPM for a key derivation, and with those derived keys, you can do encryption, decryption, signing. You can do sealing, which is encryption plus some conditions, like encrypt something in a way that it can be only decrypted when your system is in a certain state. Policies, which are a set of rules that must be satisfied to authorize access to some object or to some operation. the PCRs, which are the platform configuration registers, these are a set of special registers that contain hash values, and normally these can only be extended by hashing another hash to the already existing hash. And with this, you can do measurements at boot time, and these hash values will represent the state of your system at runtime, so you can use it for integrity checking and attestation. And the TPM also provides some very limited generic purpose non-volatile storage. I want to talk a bit about hierarchies, which is another TPM concept. So you can think of a hierarchy kind of like a namespace, and its main purpose is to do role separation between the various parties that interact with the TPM. So each hierarchy looks like this. It contains a hierarchy seed, which is stored persistently, and from this you can deterministically derive primary keys, which are not stored persistently by default, and from these keys you can derive further child keys. And there are 4 hierarchies in the TPM. The first one is the endorsement hierarchy that's owned by the TPM manufacturer, and with the primary key derived from the seed of the endorsement hierarchy. So for the key that's derived from this seed is called the endorsement key, and what the TPM manufacturer will do is that they will create a certificate for this key and put it into the non-volatile storage of the TPM. So later a client can actually verify that it's talking to a genuine TPM by that manufacturer. The platform hierarchy is owned by the device manufacturer. The owner hierarchy is for the end user or the admin of the end product. So you can use this for things like storing disk encryption keys. And the null hierarchy, it doesn't have an owner, it doesn't have any persistent state. It's just used for transient operations. So how to communicate with the TPM? The easiest way to start is by using the TPM2tools package, which is a collection of high-level commands like getting a random number, signing a message, which make it much more easy to talk to the TPM when you just want to try it out. And this package builds on the TSS, which is the TPM software stack, and the reference implementation of this is the TPM2TSS library, which contains many layers that build on top of each other. We don't have time to go into all of these details, but it's a lot of stuff going on there. Going one layer lower, the TPM supports 2 software interfaces. A FIFO buffer is used for discrete TPMs, and a CRB is used for a firmware TPM. The CRB is a command response buffer. It's a memory mapped interface. So from the client's point of view, it's kind of like an MMIO region. And it looks like this. It consists of 3 areas: the locality support, control, and buffer area. We will get back to these a bit later. And there is such a CRB memory region for each locality. So what's a locality? It's a way to represent the source of the command to the TPM. So you have multiple software components in your system, and by associating each component to a certain locality, the TPM can know where the command came from. And usually there are 5 localities implemented from 0 to 4. And locality 4 is special because there are certain commands that can only be requested at locality 4, so this should be protected somehow. Going one level lower, for the discrete TPMs, you have various hardware interfaces to access it. So the piece that's connecting together what we have talked about so far is a specification by ARM. The full name is a TPM service command response buffer interface over FFA, and it's this specification. So what it does, it defines an abstract TPM service and defines certain functions that you can use to access this. And this TPM service is firmware running within an FFA secure partition. And the set of functions that you can access are on top of FFA. And this spec also mandates that this TPM service has to provide the CRB memory regions as described by the TPM standard. So by this, what you achieve is kind of like a TPM CRB front end, but this specification doesn't say how you should actually implement the TPM command processing. So what this allows is to either have a firmware TPM when the TPM processing code is running in the same secure partition, or you can do kind of like a proxy solution when the incoming CRB commands are translated and sent out on an SPI bus to a discrete TPM. But from the client's point of view, this is invisible. So this diagram is from the spec. I won't go into all of the details, but this is how communication looks like for the TPM CRB over FFA. Here you have the client, here you have the TPM service running in the secure partition, and this is the CRB memory region. First, there is some version discovery and feature negotiation going on. And then finally, when the client wants to talk to the TPM service, it first has to get access to that specific locality. So it will store a locality request in the CRB region. This is when this locality support area is used. And then it will send one of the FFA functions defined by this spec, more specifically this FFA TPM start method. So this is special because it's not only part of this specification, but it's also standardized by ACPI now. And in FFA terms, this is a direct request that will allocate CPU cycles to the endpoint execution context. So what this means that this is how the SP can actually get CPU time to run. So when the SP is running, it will read the incoming request, grant access to the locality, return back to the client, and then the client will write, first check the response if it has the locality access granted, then write the actual TPM command that it wants to run, and also flip the start bit in the control region, so the control area. So this is where these two are used. This is where the TPM command structure will go into. And then again use the TPM start method to start the service. It will process the command, send it to the TPM backend, write back the results, and then return to the client. So this is the basic message flow of how TPM CRB over FFA uses FFA and the CRB memory regions together. And finally, this specification allows use of FFA notifications, which is a mechanism to asynchronously notify the client about some event, like end of a long-running operation, but this is not supported in trusted services yet. So moving on to the implementation, I have used the MSTPM 2.0 ref library as a TPM backend. This is the official TPM 2.0 reference implementation made by Microsoft and the TCG. So here you can see the high-level architecture of the library consists of a core part which is responsible for actually parsing the commands, processing them, and creating the response. And it relies on a crypto library, but that's implemented in a bit of a weird way, because for some of the crypto operations, it's using an external crypto library. So for hashing and symmetric crypto and so on, by default, this is OpenSSL. But for some other crypto things like asymmetric encryption, key derivation functions, those are implemented in this library itself, which makes it a bit difficult to replace the crypto operations in this library. It also has some platform dependencies, like non-volatile storage, access to some entropy source, clock source, and so on. So this is the actual implementation in trusted services. This is the fTPM secure partition, and it contains the libsp, which is our component for handling the incoming FFA messages. This here is the implementation of TPM CRB over FFA specification. And the CRB memory regions are defined in the SP manifest. This is necessary because the SP is running in Securia 0, so it cannot manage its own translation regime. But by defining it in this manifest file, the SPMC will take care of mapping these regions for the SP at boot time. Locality 0 to 3 are defined in, or are located in non-secure memory, and locality 4, as I've mentioned, it needs to be protected, so it's in secure memory. The contents of the CRB, so the incoming TPM commands are then passed to the MsTPM backend, where I have replaced the default OpenSSL with MbedTLS, but this is only for where it requires an external crypto library, so for hashing symmetric crypto and big num operations. Regarding platform dependencies, I have implemented only the minimal necessary platform porting to be able to test on the FEP base model. For non-volatile storage, I have added a PSA storage client to MsTPM, so it can use the PSA internal trusted storage or protected storage SP from trusted services. I didn't modify the internal representation of how MsTPM handles non-volatile storage. So currently it's just stored, all of the data is stored as one single 16K entry. So there is some room for improvement here, definitely. MsTPM requires an entropy source that's provided by MbedTLS, which in turn relies on a TRNG device that's mapped into the SP, again using the SP manifest. For clock, I'm just using the generic timer defined by the A-profile architecture. But as I've said, platform-specific details are kind of out of scope for my work. This is just the bare minimum for testing, because there is another team at ARM who is working on porting these to real hardware and real-life platforms. So they have more information about those details like key provisioning and so on. So for end-to-end testing, I was using this setup. TPM2tools is a convenient way to just test if the TPM works and issue some commands. It relies on TPM2 TSS library, which accesses through the bus the ABRMD, which is the access broker resource manager daemon. And this is the component that will actually open the character device, and then we end up in the Linux kernel. In kernel, there is a TPM class that's implemented by many drivers. Out of these, I have used, of course, the TPM CRB driver, which has been upstream for a long time. It's the same case for the FFA driver, but the piece that's connecting these two together, so the kernel implementation of the CRB over FFA protocol, that has been recently done by other folks at ARM. I think it will be part of the next release. I ran into some issues regarding ACPI, because the upstream CRB driver requires ACPI to start. And I wanted to test on a device tree-based system. So I made some workarounds to enable this, but those are just workarounds, so not upstreamable. I'm not sure if a use case like this will be ever needed or it will be done upstream. Regarding the rest of the system, I'm using trusted firmware as the SPMD, the Rust SPMC, that's Securia 1 FFA SPMC, and finally the secure partitions from trusted services. And with all of these put together, when I issue a command from TPM2tools, goes through all of these other components, and it works. So I want to mention this ongoing investigation that I'm doing regarding replacing the crypto operations in MsTPM with PSA Crypto API calls. This is just an investigation. It might not be feasible to implement it in the end, because there is a fundamental misalignment between how MsTPM and PSA Crypto handles keys or key material. So in PSA Crypto, the idea is that the client never gets access to the key material itself. For the API calls, it only uses a handle to refer to some key. But MSTPM, because of the in-house implemented crypto, it requires direct access to the key material itself to do the key derivations and so on. So what I did was I started mapping the TPM concepts to PSA concepts to see if these two could be aligned somehow. So the first idea is that the hierarchy seed can be represented with PSA key ID, PSA key with a well-known ID. And from this key, we can use the PSA key derivation to derive the primary keys, because this API allows a secret input, like an ID of an input key. And with this, we can do the key derivation without the seed or the primary key, private key material ever leaving the PSA Crypto implementation. The rest of the key attributes have to be input as a, or the hash of the attributes has to be input as a non-secret input to the key derivation. So this looks fine. For the transient and persistent handles and the TPM to evict control, we can just do this with PSA key lifetimes, which is basically the same concept. But then I ran into some issues because for the child key generation, the TPM spec actually requires that the child key, the private part of the child key must be exported wrapped, meaning that it should be exported in an encrypted form when it's encrypted by the primary key from which it has been derived from. And this is something that's not supported by PSA Crypto yet. I think it's on their roadmap, but it's not there. The other issue was that TPM spec requires a specific key derivation algorithm, which is a part of PSA Crypto, but not implemented by MbedTLS yet. And then I also ran into some issues. I was able to derive ECC keys from the seed, but not RSA keys for some reason too. So this is something, again, to look into. And finally, I want to mention the Opti fTPM TA, which is an already existing open source fTPM solution for ARM platforms. It's an Opti TA using the same MSTPM library as a backend. They have replaced OpenSSL with the T-Crypto API calls. And the key differences are that this solution doesn't support the standard CRB interface. So it doesn't have locality support because it uses another driver in Linux, this fTPM-T, which is a kernel client of the Opti driver. So the communication is different. The benefit of this is that actually it doesn't rely on ACPI because Opti already has its own discovery mechanism. So this driver can discover the TPM TA using that. Also, it's a more mature solution with a wider support in the ecosystem, but also it's less portable because it requires Opti running in the secure world compared to just any FFA compliant SPMC. With all that said, there are no plans for this solution in trusted services to replace this Opti TA solution. And yeah, that's what I wanted to say. Do you have any questions? Yeah. Should I bring the mic?
Thanks. Two questions actually. First one is about the discovery. You told us about the difference between ACPI and device tree. So I was under the impression that we had FFA bus now with a way to expose multiple grids in a secure partition with the newest versions of FFA. So isn't that something we can leverage here and rely only on the FFA bus and the grid and get rid of ACPI and device tree completely for discovering this service?
That was my first question when I was starting look into these things. Actually, the CRB over FFA specification doesn't allow this, so it requires that the CRB regions are statically allocated, and there is a carve out that's already known at build time, and also the upstream TPM CRB driver just won't start if it doesn't get that specific ACPI entry. So it's not like for the other clients of the FFA driver, it works like if there is the client driver will just register itself on the FFA bus, and once a partition with that specific UUID or a compatible UUID is discovered by FFA, then it will just initialize the client driver. This is not how this is implemented. So the TPM CRB driver will only start if it sees that entry in ACPI, and then it will check if the partition with that UUID is actually available on the FFA bus. So technically it should be possible, but it's not how it's implemented upstream.
Okay.
Does this answer your question?
Yeah, well, so okay, I understand now. Thanks.
Yeah, we can get back to this offline maybe, but yeah.
And maybe the second question is actually related. So you told us some of the locality regions are in non-secure memory, but now I think I understand why, but I was wondering, is that because you need to describe the regions to the kernel?
Yeah.
Okay.
So for locality 0 to 3, those are in non-secure memory, and those are used by the non-secure components. And locality 4, that's in secure memory. So that's only accessible for secure word components.
But in theory, I guess with the FFA shared memory services, we could do that dynamically and without any predetermined address, right?
Yeah, again, my thoughts are the same, but the way so this specification simply doesn't allow it, and it's a matter of changing the specification and not a technical obstacle.
Okay.
So, but I don't know if there are plans to change this specification. That's outside of my scope.
Okay. Yeah. Thanks for the explanation and the presentation.
You're welcome.
You mentioned a buffer, I guess, that it needs to be defined in the device tree, right? For the partition, the secure partition.
Yeah.
What's the purpose of that buffer? Is it shared between non-secure and secure world?
Yeah. So these buffers are actually the memory regions where the CRB structures are located, and for the purpose of that is for clients to communicate with the fTPM. For non-secure clients, they can communicate through these localities from 0 to 3, because those memory regions are defined in a non-secure memory. And for secure clients, they can communicate, or they can use all of these, but normally they would want to use the carve out in the secure memory.
Okay, so depending on the locality, you change the memory attribute over there.
No, all of these exist
in the
parallel.
SP manifest, do you change the attribute depending on the locality?
There are multiple memory regions defined, one for each locality. Right. So each locality has its different CRB memory region. Okay. So kind of this structure has 5 copies in your memory, 4 copies in non-secure, 1 copy in secure, and because of this you have different or separate entries for all of these in the SP manifest.
All right, perfect, thanks.
Any other questions? Okay, if not, thank you for your attention. Where is the last slide? Thank you. Bye.